Alright, so just reviewing direct and inverse variation real quick. Y varies directly as x um, if their relationship can be described like this. Y is x times some constant, right? So the bigger x gets, the bigger y gets, or the smaller x gets, the smaller y gets. Another way of saying this is that y is proportional to x. Y is directly proportional to x. If y varies inversely as x, or as some people say indirectly, if y and x have an inverse relation, then uh, y is equal to some constant divided by x, um, or you can think of it as some constant over x. Okay, so the bigger x gets, the smaller y gets. Um, a combined variation would be uh, just a combination of direct and inverse variation. So if z uh, varies directly as x and inversely as y, then we can say the relationship is z is some constant times x over y, right? So it's a, maybe I should rewrite these. Uh, y varies directly as x. We've got y and x, and you just multiply x by some constant, like 3 or 10 billion or whatever. Um, y varies inversely as x. Y is some number over x, right? And then if now I have to say z because I want to use two numbers. So if I say z varies directly as x and inversely as y, then I just do x over y and multiply them by some constant. All right. So let's try decoding some combination or some combined variation problems. Let me practice talking first, and then we'll practice doing some math. Okay, so combined variation. So there's gonna be a bunch of words and numbers, but we'll make it all clear. The time it takes, the true story. The time it takes a satellite to make one orbit around the Earth. Okay, so we've got the Earth. Here's a little North America or possibly India. There's a satellite up there. Um, the time it takes to make one orbit like that around the Earth varies directly as its height above the center of the Earth. So, center of the Earth up to the satellite, and inversely as its orbital velocity, the speed at which it orbits the Earth. Okay, that's what's going on. Okay, um, so let's draw that out. So the height, all right, so the time. What are we doing? Time. The time it takes the satellite to make one orbit. So let's say t is equal to. Okay, it varies directly as something and inversely as something. So we know this is so it's both direct and inverse. So this is a combined variation. So we're gonna have some constant times a ratio of other quantities. So it varies directly as its height above the center of the Earth. So we could call that height, or we could call that the radius of that circle that it forms with the orbit. So let's call that r for the radius. If you draw from the center, the very center of the Earth, all the way up to where the satellite is, um, we call that radius. That's different from its altitude above the ground. You know, the ground is already some distance away from the center of the Earth. The altitude would be, a smaller quantity like that above the surface of the Earth. I have no idea if this is way too small to see, but hopefully this will be clear in a sec. Okay, so the time it takes a satellite to make one orbit around the Earth varies directly as its height above the center of the Earth, which we're going to call r, which stands for the radius, and inversely as its orbital velocity. So let's just call that v. Okay, so this is our basic relationship. We're going to have to fill in the holes here. Time equals some constant times the radius over the velocity. Okay, if the International Space Station orbits at 6,750 kilometers above the center of the Earth, like from the center of the Earth up to where it's orbiting is 6,750 kilometers, which equates to 380 kilometers above the surface of the Earth. So its altitude is 380 kilometers above the surface of the Earth. Travels at an orbital velocity of 7.68 kilometers per second. These are all true numbers. And completes an orbit in 92 minutes. How high would my orbit be if I completed an orbit in 12 hours flying at 3.87 kilometers per second? So what we can do is we're given time, we're given radius, and we're given velocity. What we're not given is k, the constant. So we can plug in these numbers that we have and then solve for k, and then we can use that to figure out the answer to this question. So let's do that. So instead of saying time, let's say what the time is. So 92. So our time will be in minutes. So 92 minutes is equal to some constant times radius is 6,750, and the velocity is 7.68 kilometers per second. Okay, so we're measuring our radius in kilometers, our velocity in kilometers per second, and our time in minutes. And the constant here will make it so that it's okay for us to use minutes, even though the other stuff is measured in seconds. That's fine. Okay, but from now on, when we use this equation, after we figure out k, that'll only apply when we're measuring time in minutes, which will be important in a sec. So let's figure that out. So to solve for k, we just divide 6,750 by 7.68, and then we divide. What are we doing? Then we divide that from 92. Okay. So we're going to get some number times k equals 92, and then we'll divide that 92 by that number. So let me just do all those steps on the. So we'll do 92 divided by 6,750 over 7.68. So we'll do that division, and then we'll divide it away so that k is by itself. Divide both sides by that number, and this is what we'll get. So k is 0.104675555 repeating. So let us just round that to 0.10467. 6. So k is equal to was that 0.104676. Okay, now that we know what k is, we can write our equation with that constant. Okay, so how high? So the question is, how high would my orbit be if I completed an orbit in 12 hours flying at 3.87 kilometers per second? Okay, so we have the time. It's 12 hours, which we're going to have to convert to minutes. And we've got velocity. We've got the constant now. We only don't have r. We don't have the radius, because the question is how high. So the time is 12 hours. 12 hours. There's 60 minutes for every hour, so I'm going to multiply that by 60. So our time actually is going to be 720, minutes. So I'm doing this orbit, just me, out, I guess, in a spacesuit or something. I complete an orbit in 720 minutes. So I'm presumably much higher somewhere here than the space station. Equals some constant, so the constant we figured out was 0.104676 times r, which we don't know, and the velocity is 3.87 kilometers per second. So now we can solve this for r. So what I can do is I can divide both sides by that constant, and then multiply by 3.87 to get r. So let's see. So I'm going to divide 720 by our constant. So that's about, so if I divide this stuff away, just going to, yeah, etc. From both sides. I'm just being kind of lazy here and not writing out all those numbers. I get 6,878 roughly. And that is equal to my radius, my distance away from the center of the Earth, over my orbital velocity. So now I can multiply both sides of the equation by 3.87. So I'm just going to multiply what I got from the last calculation by 3.87. So my radius is 26,619. Is 26,619 kilometers. Okay. So the question, so that's the radius. So that's my distance from the center of the Earth. I'm like out there somewhere or something. Okay. The question is, how high would my orbit be? I guess I could answer that with, I didn't specify how high above the center of the Earth or how high above the surface of the Earth. This is how high I am above the center of the Earth. The surface of the Earth we could figure by subtracting 380 kilometers from 600,000 or 6,750 kilometers. Let's do that. Let's might as well. So the space station was orbiting 6,750 kilometers above the center of the Earth, which is 380 kilometers above the surface of the Earth. So minus 380. So the distance from the center of the Earth to the surface of the Earth is, on average, about 6,370 kilometers. So I could take this number, my distance from the center of the Earth, and subtract my distance, the radius of the Earth, and get, I'm about 20,249 kilometers. So my altitude is 20,249 kilometers. That's how high I am above the center of the Earth, or how high I am above the surface of the Earth, right? So I'm over 20,000 kilometers up there in space, which is quite a bit higher than the space station, which is why I can fly so much slower and why it takes me so much longer to go to orbit the Earth. Alright, let us do this one. The gravitational force between two objects varies directly as the product of their masses and inversely as the square of the distance between them. So we could say force, this is also a true story, force is some constant times, okay, varies directly as the product of their masses. So we could say mass 1 times mass 2. So it varies directly as that, but inversely as the square of the distance between them. So inversely is the distance between them squared. Okay? If the force I, who am 70 kilograms roughly, exert on a 680 kilogram polar bear, okay, everything with mass exerts a gravitational force on everything else with mass. So you exert a force on the sun, I exert a force on this book next to me. A neutron star 2 billion light years away exerts a force on me. Anyway, okay. If the force I, who am 70 kilograms, exert on a 680 kilogram polar bear at a distance of 10 meters is defined as 1 gram bear unit. Okay, my name's Graham. So 1 gram bear unit is defined as the force that I exert on a 680 kilogram polar bear at a distance of 10 meters. Okay, kind of a silly example, but I wanted to invent a new unit and show you how to do that. How many GBUs, gram bear units, do I exert on the sun, which has a mass of 2 times 10 to the 30th kilograms and is 1.5 times 10 to the 11th meters away? So let's use the information that we have first, and then solve this problem. Uh, so the force here is going to be 1 gram bare unit. So 1 is equal to some constant times the product of our masses. So I'm 70 kgs. That bare is 680 kgs. And then the square of the distance between us, 10 meters, 10 squared. Alright, so we can solve for k just by doing 70 times 680 on the top divided by 10 squared, and 10 squared is just 100. Okay, and then to solve for k, we just divide that from both sides. So k would be 1 over what we got here. K is 1 over 476. Alright, so our equation when we're dealing with force as expressed in gram bare units would be force is equal to, so I'm just going to remove this k and put 1 over 476. That's we've experimentally determined what that constant is. Now, no one else in the world uses this unit, gram bare units, because I just made it up on the spot. Usually newtons, that's a pretty common one, and that would have a different constant here. Yeah. So okay, so this is our constant if we're gonna measure force in GBUs. All right. So how many GBUs do I exert on the sun, which has a mass of 2 times 10 to the 30th kilograms and is 1.5 times 10 to the 11th meters away? So we just say, so we're going to do 1 over 476, that's our constant, times the product of our masses, so 2 times 10 to the 30th. I don't need to do the caret if I'm writing this out by hand. And my mass is 70 kilograms still. The bear didn't eat me. Oops. Sorry, I started thinking about that bear and then. So we're multiplying our masses. So 2 times 10 to the 30th times 70, and then we're taking the square of the distance between me and the sun. 1.5 times 10 to the 11th squared. Sorry, this is pretty messy. Maybe I should write again. So 1 over 476, which based on the first data we determined, times 2 times 10 to the 30th kilograms. That's the mass of the sun, quite gigantic. Times 70, that's my mass. It's pretty paltry compared to the sun. Over 1.5 times 10 to the 11th meters away. The sun is very far away from me, and vice versa, squared. So all I need to do is type all that in the calculator. So we've got 2 times 10 to the power of 30 times 70 divided by, I'm going to put this in parentheses, so this is divided by all this. Divided by, and I'm going to do parentheses again because I need to raise all this to the power of 2. So just like here, that's now I'm typing in these parentheses, so 1.5 times 10 to the power of 11 squared, and then we're going to times that by 1 over 476, or i.e. divided by 476. So that is equal to, what is that, 13 million 71, or 71,895 GBUs. Quite a bit stronger than the force between me and the bear. Alright, good luck on your combined variation problems.